Good afternoon, everyone. Yesterday, we looked at average rates of change. So now we're going to talk about instantaneous rates of change. And to get an idea of what the difference is, we're going to start with an example right away. This is based off the one we did yesterday as well, right? So the height of a ball thrown into the air can be approximated by the equation h of t equals negative 5t squared plus 20t. Determine the speed of the ball at 1 second after it is thrown. Okay, key thing there being at, right? This is not the average rate of change over the first second. I want to know at the exact moment, 1 second after it gets thrown, what is the speed of the ball right now? Okay, which again ties into the idea we talked about yesterday with the car, right? You know, if the average speed of a car on a trip is 66.6 kilometers per hour, that doesn't mean the car was always driving at that speed. It was probably driving above it sometimes, below it sometimes, right? What if I want to know the exact speed of the car at a particular moment? How do I do that? Okay, so that's what this is asking us to figure out. What's that exact speed at 1 second? So to show us this is going to come from, we're going to switch over to the graph of this function for a moment. Okay, so right, it's a quadratic, so I got a parabola. It opens down. Okay, and I've highlighted in blue. This is my target point. Right, I want to know what's the speed of the ball at this time. Right, the location of the ball, right, is 15 meters in the air. Okay, but it doesn't tell me how fast it's going. So one way to think about this, again, if you've taken some science classes, you may have done this as part of an analysis. If I want to know the speed, right, I kind of want to know what's the slope of the curve right here. So one way I could do that would be to draw a line that just kind of barely touches the curve. Okay, it doesn't cross it twice, it just kind of skims past it. So that's called a tangent line. And so that's in the green dashes here now. So that's what I'm hoping to see, right? What's the slope of this line? So I could use the graph and draw that on the graph and then find myself a couple points. It looks like there's a point here. I've got 2 points there. I could figure out the slope of this line and I'd be good to go. Okay, so that's one way we could approach this. Another way we can approach it, okay, a little more algebraically, is if I start zooming this in, okay, you can see there's some separation right now between my function and the tangent line. But if I zoom this way, 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 way in, okay, the function, for all intents and purposes, becomes straight over a really tiny interval, right? If I turn off the tangent line and turn it back on again, I can't really tell the difference. It looks like they're the same. Okay, so again, over a tiny interval, okay, the function is essentially a straight line. So if I'd like to get an idea what the speed is at that time, I really just need to do my average rate of change over a very small interval. And that will be sufficient to figure out what's going on. Okay. So let's start working that through. Okay. So for my first attempt at this, I'm going to pick a small interval. Let's say we'll do 1/10 above and below my target line. So my first interval will be from 0.9 to 1.1. Okay, it has to be balanced. You have to have equal amounts on both sides for this to work. Okay, so we go to our equation that we were using yesterday for the average rate of change. So the change in height over the change in time equals h of time 2 minus h of time 1 over time 2 minus time 1. So that's going to be h of 1.1 minus h of 0.9 over 1.1 minus 0.9. Okay. So I need to work out what's h of 1.1 and what's h of 0.9. Okay, so h of 1.1 is 15.95. Right, and again, I'm doing that by plugging 1.1 into my original equation and working it through. Okay, minus, that's h of 0.9. Okay, that is 13.95 over 0.2. Okay, when I subtract the top, I get 2 over 0.2. Okay, and in this case, I get 10. Okay, so it looks like it's 10 meters per second. Okay, to make sure that I've got this right, I'm going to do this again over a smaller interval. So let's say my new interval will be, we'll go 100th on either side of 1. So 100th less is 0.99, and 100th more is 1.01. Okay, so do a small interval and see if it agrees. If it does, I know I'm good. If it doesn't, then I have to keep going smaller as I go through. So we'll set it up again. So my change in my height or my change in time is going to equal h of 1.01 minus h of 0.99 over 1.01 minus 0.99. Okay, so 15.0995 minus 14.8995 or 0.02. Okay, when I subtract the numerator, I've got 0.2 or 0.02. And so that is equal to, that's also equal to 10. I divide that out. Okay, so my two answers agree, and I'm good. Now, I'd like to point out that I think yesterday when you did the average rate of change between 0 and 2, which is also a balanced interval around 1, it happens to work out to 10. Okay, in general, that doesn't work. Okay, it might just be because it's quadratic, but that doesn't always work. Okay, but that's the idea of the process. Is if I want to find the instantaneous rate of change, I just do my average rate of change over a very small interval. Okay. So we're just going to go through this process again with a different function. So again, this example is coming, we think we did this one back in the trig unit with the tides or something like it. So the height of the tides in the Bay of Fundy can be approximated by the equation h of t equals 6.5 sine of pi over 6t, where h is the height of the water and t is the time in hours since the ocean rose to sea level. How fast is the water rising as it reaches sea level? Okay, so again, to get a quick idea of what I'm going for here, okay, it's a sine function, right? Amplitude is 6.5, so it goes 6.5 above and below. Okay, pi over 6, so that means the period is 2 pi divided by pi over 6, okay, which is 12. Okay, again, that's not super important for the rate of change. Okay, but right there's my rough sketch of my graph. It says, how fast is the water rising as it reaches sea level? Okay, so we could either use 12 as our target point, or we could use 0, which is pretty easy to work with, right? Or we could keep going, use 24, wouldn't really matter. Okay, but for the sake of keeping it easy, let's use 0. Okay, so I want to find the slope here. Okay, so we do the same kind of an idea. Let's start with something, a small interval, but not too small. So again, let me say 1/10. So our first interval will be from negative 0.1. So again, I'm using 0 here as my target, to 0.1. So my function again was a height function this time. So t equal over t. So h of 0.1 minus h of negative 0.1 over 0.1 minus negative 0.1. Okay, let's see what we get. Okay, and again, if you're following along on your calculator, make sure you're in rad mode. Okay, right? Make sure you're in radians in order for this to work. So 6.5 sine pi divided by 6 times 0.1. Okay, now to keep this accurate, I'm going to use a bunch of decimal places here. So I've got 0.3440183715 minus, and actually I think the sign, when I put in the negative, I should get the same thing, just negative. Yes, negative, same decimal. 0.340 and so on. Okay, and this is over 0.2. Okay, so that actually works out quite nicely, right? When I put these together, I'm not going to add them. I'll have 2 of them, and then just dividing that by 0.2. So this is going to work out to 3.4018 if I round it to 4 decimal places. Okay, so there's my average rate of change over that interval. Okay, let's do a smaller interval and see if it still agrees. Okay. So my next interval, we'll go hundredths again. So 0. Right, negative 0.01 to 0.01. So the change in the height over the change in the time is equal to h of 0.01 minus h of negative 0.01. Okay, and so on. So okay, I'm just going to run this one through my calculator, okay, and see what I get. Okay, so when I run it through this time, I end up with 3.4033. So if I round it, it would be 0.34. Okay, this is different than when I got the first time, right? I mean, obviously they're both about 3.4, but to more decimal places, they've changed. Okay, it's a little bit different. So to verify that this is the rate of change, okay, I'm going to do it again. So I'm going to go to the smaller interval now and see what happens. What if I do this between negative 0.001 and 0.001? Okay, what happens? So same process. H of 0.001 minus H of negative 0.01, okay, over 0.001. Okay, so what do I get this time? Okay, and this time when I run this through to 4 decimal places, they actually agree. Okay, I get 3.4034. If I go to more decimal places, they don't quite agree still. Okay, but that's probably pretty good. All right, so long as they agree to a few decimal places, you're probably okay. So my instantaneous rate of change is about 3.4, 3.4034. Okay. Yeah, that's basically the process. It is just doing the average rate of change over small intervals around your target point until they agree. Okay, so that's it for this lesson. That's how you calculate an instantaneous rate of change. There's the homework. Okay, just one quick thing to note about the homework. Some of the questions will ask you to find the equation of the tangent line. Okay, but it's the same thing as what we talked about yesterday with secant lines. Right? If I really want to find the equation of the line, right? So for the equation of a tangent line, right? It would be like that last example we did in class yesterday, right? You would find your slope by using the rate of change, right? And then you would find your y-intercept by using the point, right, your target point, and plugging it in for x and y. Okay. So again, like yesterday, the homework's coming from a couple different sections in the textbook because this really applies to all the different functions we've learned about. So there's some questions on page 71, on page 190, and page 298. Okay. Thank you very much for watching, and I will see you tomorrow.